Hi there, my name is John Ceribes, and this is my Lab 2 video report on projectile motion. Start, here are some of the basics info about projectile motion. The system in this situation is a foosball thrown across a room, moving horizontally and vertically. The surroundings are everything else acting on it. The two forces acting on the ball are gravity, which is constant and points down, and drag, which opposes the ball's velocity and grows with the square of its speed. Here are the key equations I'll use throughout this lab. The force of the gravity is mg downwards, Newton's second law, so acceleration depends on net force divided by mass. The drag force is proportional to the square of speed and points opposite the velocity's unit vector. The matter is here because unlike a straight drop, the ball's velocity direction is constantly changing, so drag has to update in both y and x as time goes on. The purpose of the lab is to track the motion using a foosball being thrown using tracker, build two computational models, and then each of those has one with gravity and then one with gravity and air resistance, and then comparing those models against real data and seeing how the real data and the new data affects accuracy and terminal velocity. So for my experiment, the system was a foosball with a mass of 12 grams. I threw it left to right. It went up a little bit, so I had an arc, and then I released it about 0.8 meters above the floor. I calibrated everything using tracker and a tape measure, which was 1.092 meters. Yeah. Here's a tracker analysis. On the left, you can see the video with the ball's track positions marked frame by frame going down the staircase. On the right are resulting x and y position graphs. The x position increases steadily the whole time, while the y position rises, peaks, and then falls. Yeah. This table shows the actual track data. The ball starts at a height of about 0.8 meters, climbs to a peak about 1.1 meters around, when t equals 0.47 or 5 seconds, and then lands at t equals 0.9 through 3 seconds, where x equals 0.7 meters. Yeah. So from our first computational model, I left out drag entirely, so it's just going to be gravity. The initial conditions match what I measured about, which is 0.012 kilograms or 12 grams, 0.798 initial velocity, 0.798 starting position, initial velocity of 1.24, and then, 4.6 meters per second, and the same delta t of 0.33 seconds. With the drag coefficient set to 0, the net force simplifies down just to gravity. So the only thing changing the ball's motion is the constant downward pull of gravity. Here are the results. Because there's no drag, x velocity stays perfectly the same at 1.24 meters. At t equals 0.93 seconds, the model predicts a final position of about 1.15 meters in x and 0.86 meters in y. That overshoots everything a lot because the x was 0.77 and then y was 0. This is because there's no drag. So my second model, I kept all the same initial conditions, but I added a drag force. I found the right drag coefficient by tweaking it just over time, and then now the net force now includes both weight and drag, where drag is calculated using the velocity unit vector, so it always opposes whatever direction the ball is currently moving in both x and y. The drag included, the results match much more closely. At t equals 0.93 seconds, the model predicts the final position of about 0.77 meters in x and around 0 in y, which is perfect. You can also see that the velocity in x now decreases steadily instead of staying flat. This shows drag is actively slowing the ball down. And then the velocity in the y direction crosses 0 near the same time as the real peak. So putting all three data sets and then looking at them together, you can see how different each of these are from each other. You can see that the one with drag is closer to the actual observed, and how that makes sense because it's really using what real life forces are acting on the ball. So what does this mean in terms of terminal velocity? Terminal velocity happens when an object's net force becomes 0 or when drag fully balances gravity. Looking at my velocity graphs, neither model reaches that point. The flight only lasts 0.93 seconds, and velocity in the y direction is still changing right up until the landing. There just isn't enough time for it to reach terminal velocity. So to find actual terminal velocity, you need a design experiment to drop it from a way higher height, maybe a building. What if the object were thrown up instead with the same initial speed? My original throw had an initial speed of 4.7 meters per second, split between horizontal and vertical components. If thrown straight up at 4.7 meters per second, the ball goes into the vertical direction instead. Since there's a larger vertical launch speed than original, it's going to stay up there higher and then come back down a little bit. So it's going to take longer to come back down. So horizontal doesn't change. Um, a few potential sources of error are going to be human error in tracker, out of plane motion, and then like calibration issues. So to conclude, foosball was thrown across a room. Yeah, I used tracker analysis on this, and then I used two different models to analyze what was actually going on. The